Attracting tomorrow. TDK.
Alright, we're back here. Now we're going to demonstrate a more advanced mode of the power strip board for an application engineer. What we're going to do is we're going to now attach the programming dongle, the I2C dongle port, and then launch our GUI software. And we're going to take the power strip board, which is in default mode for the Zinc 7 SoC from Xilinx, and we're going to convert a few of these outputs to make it look like an NXP IMX.8. And what's going to happen here is we're going to demonstrate several things. Number one, that this power strip board is very flexible and can be tailored for any FPGA and SoC between 5 watts and 40 watts. And the graphic user interface tool that you'll see here in a minute will allow you to do that very quickly. We will be releasing a future graphic user interface where you'll be able to traverse between the different FPGAs within seconds, but the current graphic interface that we have for the board today, you have to do this for each output voltage option. So that's a little commercial for the future. Alrighty, I just want to show you a couple things here as we set up our system. I've actually shown earlier how to attach the USB dongle for the to your laptop, and how to actually attach the wire to the power strip board. You can see there the ground, the SD and SCL pins there. You just have to make sure you get the ground pin correctly, and onto the power module, and then this little connector here for USB to your laptop, and then to launch your GUI. So that's now connected to my board. I've already actually powered up the board, and as I mentioned earlier, it's already set to Zinc 7 design. We're going to change that now to an IMX.8. Okay, so you can see the power good signals are good. We're going to actually change this live, each of these output voltages one at a time. So to start with the first voltage for IMX.8, you'll notice here on my PowerPoint screen, we're showing actually the Zinc 7 Design 3 and how to convert it to Design 9 for IMX.8. It turns out that the first output voltage of output voltage 1 here, and let's go ahead and go to output voltage 1 here, is already set to 1 volts, and you'll be able to see that in the meter here very shortly. And again, as we shown earlier in the previous video, you can simply just attach your meter to the ground and to the supplies, and you can see that it's pretty close to 1 volt. In fact, we're only off by 2 millivolts. So the core voltage of the IMX.8 is the same as the core voltage for the Zinc 7 on voltage 1. Now let's go ahead and go to voltage 2. We'll go to voltage 2 here, and we're going to check to see where that's at. You can see that's at 1.8 volts, and that makes sense because the Zinc 7 design, this is for the VCC aux rail. Now in the IMX.8 design, we dedicated voltage 2 to 1 volt up to 6 amps. Sometimes in the IMX.8 they like to have separate voltages for the core voltages for different power modes. So what we're going to do here is we're going to take the GUI, and we're going to go ahead and launch the GUI for voltage 2. We're going to change this from 1.8 to 1 volt very quickly, and we're going to show you how to do that. Okay, we're going to go ahead and launch our GUI interface now, called Control Center. You can kind of see the icon for that here on my screen here near my son, who's surfing in the background there. And here's the Faraday configuration control software. First thing you're going to want to do is to connect to the board. It usually takes about 3 seconds. You'll actually see the status go to power good. So you saw it go from blue to green under status power good. And you'll notice that it was set initially at base address 8 and slave address 8, meaning slave address 0. Now output voltage 2 is at 0.9, as we showed you earlier in our presentation. And so let's go ahead and go to 9 and hit start. And then on our screen you can see it actually adjusted to read that register. Again, if you're confused about what I just did there, just remember that each of the power modules was set at a different address. So here, when you first started the GUI, it was reading base address 8, slave address 0, and then voltage 2 was at base address 8, slave address +1, which is set by an external resistor on the schematic, which now is residing at hex address 09. So as we went to 09 on the GUI here, it read what was inside the programming register at 1.805. Now, going back to the eval board, you can see that now we can actually tune this to 1 volt as per our original task. So let's go ahead and go to 1 volt. And you can see it's plus or minus 5 millivolt steps when you hit 1 volt and write to the register. Now you can see on the meter it went to 1 volt, which is great. Sometimes there's some offset in there on the DAC, but looks like the DAC is pretty well calibrated in this particular part, which is great. What's happening here is when we wrote to the register, it wrote to the volatile shadow register of the FS1406 on this particular power module at this location, in between my finger there. It doesn't mean that it wrote to it. There are actually 5 memory cells inside the power module. When it leaves the factory, it should be set to an initial voltage. You have 4 left. Now in this case, if you go back to my GUI on the screen, you see you can actually burn that. And I'm going to go ahead and show you what that looks like if you hit the burn. You can see that it says you need 7.5 volts on the voltage input. So if you wanted to burn this, you can actually plug in 7.5 volts here at terminals 1 and terminal 2. And then once you do that, launch your GUI, and then you can program this to now 1 volt. In this case, we're just trying to do a quick demonstration here, so I'm not going to burn. I just want to show you how quickly we can set that to 1 volt on voltage output 2. Alright, so that's how easy it is to work with our GUI. Let's go to 1 more voltage here on my screen. We wanted to set output voltage 3. So we wanted to set output voltage 3 now here to 1.8 volts. Okay, so let's go ahead and do that. Let's go back to my meter. Let's check to see where it's at. It's going to be probably at 1 volt from zinc 7. That's correct. So we're going to set now output voltage 3 to 1.8 volts. Let's go back to our GUI on the screen. Now this is at address, going back to our addresses again, so you have this little address map, at address X0A. So you can see output voltage 3 at slave address 2 at output voltage X0A. And so we're going to go back now to the GUI. We're going to go to hex address 0A, hit start, give it a couple seconds to react. Okay, and there you go. So we want to change this to 1.8. So if you look at now the power meter on my screen, let's go ahead and now go closer to 1.8, and there they are. I'm going to come a little bit under in this case just to show you how easy this is to trim. So you can see it coming a little bit under 1.8. Now I can step up plus or minus 5 millivolts going back to the GUI. So now I'm going to continue to step up and write to it until I get a little bit closer. Just keep in mind that there's an offset on the DAC, And remember, this is a closed loop measurement here. 193. Let's continue to get closer to 1.8. There you go. We're 2 millivolts away now. That's actually pretty good. So now we've set output voltage 2 to 1.8. So you can continue to go through this exercise for each of the output voltages and then tailor your design using the TDK Faraday GUI for each of the output voltages of the board for your particular FPGA, SRC, or ASIC, or ARM core. That's a really nice quick demonstration of how to use the I2C dongle and the power strip board for an application demonstration of how to do a quick design using the power strip double board from TDK.
Attracting tomorrow. TDK.